Today, we are Group 4. Our Numerics Lab Project is determining bipolar NPN transistor characteristic curve. I hope you would like this video.
The goal of our project is to generate the NPN BJT circuit characteristic curve and compare the theoretical or generated equation of the curve with the actual series of points or data gathered through this program.
We will test a BJT in identical circuit as well, namely the 2N3904 in a fixed bias configuration. By means of a curve tracer, we can get the desired graphical representation of certain parameters that will display the characteristic curve of a NPN BJT on testing. And from the curve tracer, we can now gather data or points to plot in Python.
The numerical methods that we have used is polynomial regression. It is a form of regression analysis in which the relationship between the independent variable x and the dependent variable y is modeled as an nth-degree polynomial in x. This numerical procedure can be readily extended to fit the data to a higher order polynomial.
For all we know, a bipolar junction transistor is mostly used because of the advantages of this three-terminal solid-state device over the tube, and it is obvious that it is smaller and lightweight. It had no heater requirement or heater loss. It had a rugged construction. It was more efficient since less power was absorbed by the device itself. It was instantly available for use, requiring no warm-up period, and lower operating voltages were possible. We studied our Electronics 1 when we were third year, during the first semester, and we have learned that in a transistor, there are three basic regions of operation. These are the cutoff, active, and saturation region. The active region is the operating range of the amplifier. The transistor operates in the active region between saturation and cutoff. In the cutoff region, the amplifier is basically off. There is voltage but little current. The VCE is maximum and IC is minimum in the cutoff region. In the saturation region, the amplifier is fully on. There is current but little voltage. IC is maximum and VCE is minimum in the saturation region. These are just some general concepts about the bipolar junction transistor.
We will now discuss the circuit that we have built in order to implement a curve tracer. We have used some links or references, but we will not focus too much on that, and focus on how we gathered our data and how we have plotted it using the live plotting feature. This is our circuit, and it is composed of a DAC converters, namely the MCP4921, 12-bit DAC converter. They are used to sweep the base and collector voltages and provide the output characteristics. A 16-bit port needs to be written to the DAC to set the analog voltage. It is operating in a fixed bias circuit, and we used a 2N3904 transistor. So the schematic, the Arduino pin 11 to pin 4 of both DACs, Arduino pin 13 to pin 3 of both DACs, Arduino pin 10 to DAC1 pin 2, Arduino pin 9 to DAC2 pin 2, DAC pin 1 and 6 to 5 volts, DAC pin 7 to the ground, DAC pin 8 analog output to the base resistance or RB, DAC pin 2 analog output to the collector resistance or RC, transistor emitter to ground, transistor base to RB, and transistor collector to RC. So now, we'll discuss how the live plotting of Python works and how it communicates with the Arduino implemented curve tracer for the data gathering.
Now, for our data gathering, we've implemented a curve tracer in Arduino as a tool for live plotting. The curve tracer can generate and display a family of curves of collector current versus collector to emitter voltage, or VCE, for various values of base current, or IB. To obtain the IV curve output curves of BJT from the implemented curve tracer, it shall read the voltage drops at the transistor when separate voltages sweeps at the base and collector are applied by using a DAC converter, which have been mentioned a while ago. We'll explain how we did the live plotting and how we get our data from Arduino. First, we have to let Arduino communicate or talk with Python. By the way, we used Python 2.7 for live plotting because of the legacy software and libraries that is available and not found in Python 3. Now, we'll explain our code for live plotting. We've imported serial, NumPy, matplotlib, and drawnow for our libraries. And voltage, we assign voltage object as an array, current object as an array. And the data from Arduino will be coming from serial port to Python. And we cannot have more than one thing looking at the serial port, so we cannot listen to serial port at the same time, both for Arduino and Python. The data we're gonna bring from Arduino and graph in live using Python, specifically drawnow. Creating our serial object data named Arduino data, and the serial port is located at COM4 with a baud rate of 9600. And we should tell matplotlib that we want an interactive mode to plot live data. We also created a function that make our desired plot rather. We will show the plotting between voltage and current, and we also show the grid of the graph. We've also labeled x-axis as voltage and y-axis as collector current, naming the graph as characteristic curve, and we also put legend for our plotting. We created a while loop too. While true loop is used for a while loop that loops forever. While Arduino data in waiting, when Arduino data is not found or equal to 0, it will function that there is no data coming from Arduino and will do nothing. Arduino data read line functions as reading the line of text from the serial port COM4, and we split our data string into an array named data array. We converted the first value to a floating number and named it in VCE. Also, for our second value to a floating number and put it in IC. Build our voltage array by appending VCE reading, the append function as adding item continuously. And we build our current array by appending IC reading, the append function adding item continuously. We've called drawnow to update our live graph. The plot will pause for a 0.00001 seconds for interval. If there is an active figure, it will update and display before the pause. And for checking, we printed voltage. Now, we will show you the live plotting. And we will now run the live plotting. This is the live plot of Python. And for checking, we printed it too. This is the first characteristic curve, and now it's plotting the second characteristic curve. These are data of arrays that we got from Arduino. Now it's plotting for the third characteristic curve. That's the fourth characteristic curve. And it's currently plotting the last characteristic curve. As you can see, the plot goes back from 0 or the origin. And now it will now repeat the first characteristic curve. And from there, we can stop plotting because we already got our 5 datas for our characteristic curve. And we will transfer it in Python.
The data we have obtained from the live plotting feature of Python from the Arduino curve tracer is transferred to the Spider Python environment for us to check the series of points and plot it through matplotlib and using the polyfit. We already got the equation for each characteristic curve using regression. I'll explain briefly the codes for the Spider Python. So we have load the data arrays gathered from the live plotting feature. And we have 5 VCEs and ICs for the 5 characteristic curves. So we defined 7 functions, 8 rather. So this is the first function. This is to display the first characteristic curve from the series of points gathered from the data and display or determine the equation, summations, and the correlation coefficient using regression. So defining the size of the array, our n is 50 because this is all 50 and 50. So this is the data gathered from the curve tracer of the first VCE and IC. Here we use the mat.fsum for the summation of x, mat.fsum for the summation of y, for the summation of xy, for the summation of x squared, for the summation of y squared, and this is for the correlation coefficient or R. So from here, we got the equation or the np.polyfit and plotting and displaying outputs, we use the plt.show. So we print the R, the correlation coefficient, the summation of x, the summation of y, the summation of xy, and the equation. So we use the same algorithm here for our second characteristic curve, and so on until the fifth characteristic curve. So now, we will combine all the curves. I called the function, I used the function curve show all to display the combined graphs of the characteristic curves, of each characteristic curve. So we used also a legend for the saturation and cutoff region. And here, this is our equations that we have gathered or we got from obtaining the polyfit of each curves. So this is the first equation, the second equation, and the third, the fourth, and the fifth. So we will also plot it to show the difference between the data or series of points and the equation. So lastly, this is the last function that I've called. It is curve data versus equation. So it will plot the difference between the characteristic curve data and characteristic curve equation. So now I will show the plots. This is the first plot, the characteristic curve 1. So plot of y1 of x. So this is the equation. By the way, it is in 6th order of polynomial. So this is the correlation coefficient, summation of x, the summation of y, the summation of xy, and the equations, or the polyfit or arrays that have gathered. This is the characteristic curve 2 and characteristic curve 3, 4, and the fifth characteristic curve. So here is the combined characteristic curves using the data arrays. So it shows the cutoff region is in this part and the saturation in this dotted line part. So we also called the curve equation. So this is the plot of the characteristic curve from the equations we've obtained using the polyfit. And lastly, the characteristic curve of the data versus the equation.
What we are showing is the live plotting in obtaining the IV values for each characteristic curve in time intervals. These are gathered data arrays to be plotted in Spider to verify the values of base current.
These are the data arrays gathered from the live plotting, and we will now verify the IV values using matplotlib and show the plotted data. So this is the plotted data or plotted curve. In the first characteristic curve, we got an IV value of 3 in microamperes. And for the second characteristic curve, the value is 13 microampere. For the third, the IV value is 23 microampere. For the fourth, the IV value is 33 microampere. And for the fifth characteristic curve, we got an IV value of 43 microampere. We obtained these data or this output by using np.median and calling the IV values. The purpose of getting the IV values so we can compute for the beta of the transistor using each the collector current in each characteristic curve.
Thank you for watching. Hope you like it.